Okay, so let me see. I mean, I put too many slides, so I'm a bit worried.
I can tell you in 5 minutes when you have 5 minutes.
All right. So, and this works? It's in there. Yeah, fantastic. So I don't know what I'm doing with these cables, so hope it's, I mean, I don't know. Anyway, so thank you, the organizers. Very happy to be here. The workshop has been so far great, so thank you. And for you to be here to, I mean, this is the last talk, so I'm amazed still there's some people around. Okay, so let me start by telling you a bit what one of the main activities in my group. What we do is we try, yeah, we basically study collective and individual behavior in biological systems. This is one of the things that we do, and that consists basically in trying to provide equation of motion or behavioral rules for individual biological entities that could be bacteria or sheep. And basically, then what we try to see is if we get a collection of them, if the rules or behavioral rules or equation of motions are enough to reproduce what happens at the level of the collective. So if we get the collective behavior in this system, for example, if you have bacteria, if you are going to get this, or if you have sheep, if you are going to get this kind of patterns. So basically, we try to connect microscopic and macroscopic worlds. And then the question is a bit, one fair question is why we need these physical or mathematical models for biological systems. And I think they help for two things. One is to test biological hypotheses, and the other is to test basically mechanism, basically to provide a proof of principles. And typically the main goal at the end is to extract the organizing or self-organizing principles behind the patterns that we observe, right? And one question is which kind of model should we use for doing this kind of stuff? And with this, I'm going to move to what we are trying to promote, which is, a framework, a theoretical framework where we will not consider that, these biological entities have one single equation of motion, but could have many and can adapt their behavior and so on. So the idea is very simple. I mean, what we are trying to do at the moment is we assume that this whatever active thing, biological or robot or whatever, or even a bacterium is going to have what we are going to call here the internal control system, that if you want is a kind of mini brain that is going to be within our moving entity. And that mini brain is going to be a Markov chain in the formalism I'm going to show you. And that basically mini brain is going to control which equation of motion we have to use and will control basically the behavior in physical space of these biological units or whatever, these active units. So now let me explain, and basically the whole talk will be to explain how this idea works, this formalism, and how you can go from looking at experiments, how you can construct this mini brain, and how to couple with the physical motion in physical space of these particles. So let's start with a particle that does this weird kind of behavior, moves in kind of spiral shape, then does a kind of zigzag, then this blue pattern. So what you can do, our goal is to construct this mini brain. So what we are going to do is we are going to compute for how long is in each of these patterns that we need beforehand to recognize. So suppose we recognize these three patterns. Now we measure for how long is in each of them. In fact, what we know, what we want to obtain is the distribution of time is in each of these states. And now what we are going to do is the following. We are going to say, if we are, in this mini brain, we will be in one of these nodes, and we will be doing, if you want, a kind of random walk within this network. Suppose that you are in one of these black nodes, then you use to move your particle in physical space the equation of motion 1, or you can have many equations, right? So you use this one. When you use this one, you are going to perform spiral motion in space. Then you move to one of the red nodes. If you get one red node, then what you do is you move with equation of motion 2. And if you want to the blue, you use equation of motion 3. And now, how you are going to choose what is the basically how many nodes and how you wire them, this is, you will need to do it in such a way that you reproduce these distributions. Okay, so that is basically the idea, and there is something important to realize is that you have two types of interactions here. You have interactions in physical space. This is going to be the usual force and torque among the particles, but you have also, you could eventually have interactions at the level of this internal variable, or if you want, this mini brain. What does it mean? It means that, for example, if you have one particle is in a given internal state, for example, for us, in the following in the talk is if a particle is moving, that particle that is moving may induce a change in the other particles that might be not moving. So a particle moving may see another part not moving, may see a particle that is moving and say, okay, I also will start moving, right? So they can interact that this way, and there is a coupling in the sense that I can be more influenced with someone that is close to me with respect to someone that is far away from me. Okay, so so this is what we have. I mean, and to give you kind of idea how it works more in practice, suppose this is a very, very simple example. You have particles that move to the left and particles that move to the right. They move to the left or to the right with different, let's say, speeds. And then what you can do is this one, you can represent it in a kind of, in this form. You move with velocity 1 and velocity 2, let's say, to the right, and then velocity 1 and velocity 2 to the left. And then when you are in the red, you use this equation, but basically the difference between one and the other is just this sign, and so on. So I mean, this is really a very simplified model, but I mean that I'll let you understand how it works. And this something that is good. If you neglect interaction among them and you are interested in getting, for example, the diffusion coefficient of this, if you assume that the dynamics in this Q here represent this Markov chain, if the dynamic of the Markov chain is relatively fast, what you can do is you assume that you go to the steady state of this, and basically once you are there, you can compute what is the diffusion coefficient and let's say the average bias or convective term that is going to be associated with the circuit, the mini brain that you have put in the system. So I mean, without interactions, you can solve it without any problem. Okay, so how we go then from real data to this? So let's go to apply it. The example I'm going to give you is bacteria, and we are going to look at the behavior of enteromorphic Escherichia coli near a glass surface. So when you see this, I mean, bacteria as E. coli, when they are close to a surface, you have hydrodynamic interactions and then turn to move in circular motion. So, and if there is no addition to the surface, basically what you observe is something like this. So you will see that moves in a noisy circular orbit. Now, if you think that something of interest may be sitting on that surface, that sounds like a very inefficient way of exploring the surface. So this, you may see a bacterium performing this for quite some time, but often what you are going to observe is something different. These pathogenic bacteria, what they do is they perform stop events on the surface. That is what I'm showing you here, which basically allow them to break that circular trajectories and reset the moving direction in this other way, which allows them to explore in a more efficient way the surface. So if something of interest is sitting on that surface, that sounds like a more efficient way of exploring the space. So now, because they are doing this stop event that you saw in here, every time that this circular arc stops, basically what happens is the bacterium stop. So if you look at the speed as function of time, what you can see is that the speed is high, then low, then high again, and so on. If you get the histogram of the speed, you will get that there is a local minimum, and we will use this to decide that if we are below the threshold, we are going to say that the bacterium is in non-moving or a slowly moving phase, and when it's above, we are going to say that it's in a moving phase or state. So why we want to do that? Because what we want to do is we are interested in computing the distribution of time in the run or moving phase and in the stop phase. And this is what I'm showing you here. This is in log ln, And what you can see is the distribution of run times is straight line, that the distribution of stop times is not straight line. Now what you can do is you say, okay, I have one state that is the moving and the other that is the not moving, so I can use just two states and a Markov chain. Problem if you do that is that you will get, you get an exponential distribution for the run times, that's okay, but you will also get a straight line for the stop times. So how can you improve this? You can, this is not consistent with this picture, but you can also continue insisting in using Markov chain. What you have to do is you have to enlarge your space, and now instead of having just two states, you are going to use three. And two of them will have to be associated with this stop phase. So this is, if you do that, you will be able to reproduce what are basically this kind of data. Now the problem is what are these states that we need to impose or use. Mathematically, we know that we will need them, but we want to give some evidence that they do exist if you look at you are back to the experiments. So this is what we did, and what we've realized is, sometimes when we were thinking that the bacterium was stopped, was not really stopped, was doing this. And then detaches and continue moving. So we define then when the bacteria is moving, it's in state 2, when it's doing this rotation in state 1, and then when it's state 0 is when it's stopped without rotating or doing anything. So once you have that, what you can do is you can compute for how long the bacterium is in each of these states, and you can compute how often you go from 0 to 1, from 0 to 2, from 1 to 0, and so on. Once you have that, you basically, from the data, you can reproduce, you can get all the rates associated to this Markov chain, and you have your model. So now we have a model that will tell us when the bacterium is going from these different states. So next step is we want to use this information to affect the equation of motion of the bacterium. So now the velocity, the angular rotation, you have these two. One is the update of the position of the center of mass, if you want, of the bacterium, and the other is the moving direction of the bacterium. Now, if you have these two equations, depends on this V, omega, and D, and this one adopt different values depending on the behavioral state of the bacterium. Now, of course, you can put this in the computer and simulate it, but this you can also do some analytical, this you can solve it, in fact, exactly in absence of interactions. And now you can try to get equations for the probability of finding the particle in state I in position X moving in direction theta at time t. So what you do is you take this Langevin equation and the Markov chain I mentioned before, and then you put all this together. This looks this way. It's a forward cosmographic equation with transition champs, or Fokker-Planck if you want, and you can solve it, and then you can get the diffusion coefficient. The diffusion coefficient logically depends on the structure of your network and on the transition rates. And for this case, for the circuit that we obtain for this bacterium looks this way. Now, let me show you what happens with the diffusion coefficient. This is the diffusion coefficient as function of one of the transition rates. This is the transition rate 2,0, and the 2,0, this transition rate is the one that regulates for how long the bacterium is in the moving state. So as you can see, there are two situations. Two limits that are easy to understand. One is when the K20 is very large, let's say go to infinity. That means whenever you go to 2, you go out very quickly. That means that you always stay in these blue states. So basically you don't move, and if you don't move, the diffusion coefficient is very low. The other extreme is when you K20 is 0, and that means that you will never escape from state 2, and you will be always here moving. And if you are always moving, you move in these noisy circular orbits, and you are basically not very efficient in exploring the surface. So your diffusion coefficient is not that high. So you have a point at the in between, which is the one that maximizes the diffusion coefficient. And the good news is that it's there where the bacterium operates. So operates at the K20 that maximizes the diffusion coefficient, which you can argue that is, something good for the bacterium to explore the surface. Okay, so now I move to sheep. So we left bacteria, and now we are going to sheep, and we are going to use basically the same way of thinking to understand the behavior of sheep. There will be some things that will be different, but you will see that basically we can use the same formalism. Here you have 4 individuals. Okay, I'm still on time, I guess. You have 4 individuals. So what you are going to see here is that these guys, they stay grazing, basically not moving much, and then they are going to move collectively, and typically they do forming these files, right? So they will go there, they will stay, and if you wait for a while, you will see them moving this. Oh my God. Okay, let's go again. So you will see these guys doing this, and they stop and move, and let's see how, you see that they form these files. So every time that you see a collective motion, it typically is in line formation. Okay, so now this is the same, another video, but this is experimental data. This works, hope, yeah. So you will see that what is happening, you have again the 4 individuals. There is one that is leading, that was the red individual, that was the line formation, now it's the purple individual, again, line formation, and so on. All right, so there's a few things that I want to basically focus now, is that there is these two phases that are easy to identify. We have a phase where the group is in the kind of grazing mode, not moving, staying there, and then you have a collective motion phase. This collective motion phase is going to be interrupted by another period where these guys are going to be static, grazing around, and another collective motion phase. So here I want to make, if you are more or less used to listen to people talking about collective motion, the usual way of thinking of collective motion is you are just focused on one collective motion phase. You assume that this is basically individuals are constantly on the move, that you assume that there is no leader, and usually they are constantly exchanging information on the direction of travel. So that is what typically is done. So what I want to do is to forget about that. Basically, because here we will change a bit the perspective of the problem. We will explicitly consider that collective motion phases have they start and they stop. So there is phases that have a finite duration, and which means that between you stop and you resume moving, many things could happen in there. For example, you could select who is the leader that is going to guide the group for that collective motion phase. So that means that we are not going to consider that during the collective motion phase, we cannot have any leader. And also we are going to assume that there is a negotiation that could happen from the transition from the grazing phase to a collective motion phase. And I'm going to show you that they don't exchange information regarding the direction of motion of the neighbors, what you do in the Vickshek model. So we will not take into account the velocity. We will see what they are exchanging, or important information is related with positional information, or where they are located, not in which direction they are moving. Okay, so I go to the most important question for us at the moment, which is to move or not to move, right? So this is what these guys have to decide. We have our moves, they are static, one start moving and the other may follow. That's the idea. So we go from grazing to, grazing phase to collective motion phase. So if you look here at the speed of one individual, this is individual number 1, what you see is that the speed is low, then high, low, and so on. Again, we can use the trick of looking at the speed distribution, and we can determine that there is a threshold. If we are below that threshold, we are going to say that it's not moving. If we are above, we are going to say that the individual is moving. Basically, we go to a binary signal, right? So, which is this one. And in this signal, we are interested in knowing and getting the statistic for how long, the distribution of times the individual is moving, individual number 1, and the distribution of time is not moving. So if you look at that, then this is what I'm showing you here. You have the distribution of run times. This is not log-lin, but lin-lin. And this is the distribution of stop times. And what you can see here is that if you go into using 2 states, you are fine for the run times, but again, you fail to describe the stop times. The stop times is not a single exponential. So what you can do, same thing as before, we enlarge the Markov chain and we use 3 states. And now we will need to see what happens with the transition rates that we put in this Markov chain on this network. And again, we will come to the idea that if we use 3, we will be able to describe this distribution. And the question is, what are these S1 and S2 that we need to use if we want to describe a distribution like this one? So again, we were looking at the data and trying to define what could be that. And basically, we decided to use the following. S1 is when the individual is not moving with the head down, and S2 is when it's not moving with the head up. So the head up, we are going to interpret that this is in an alert state, probably, let's say, looking for predators, something. A head down probably means that it's eating grass. So that was the idea of, now we are in that, trying to put diapers and so on the sheep, that this goes to see that what they consume and how much and so on. Anyway, so now there is something that is different from what I show you in sheep. In bacteria, is that when you see when ship 1 is moving, suppose if it's moving at this point, you see that also ship 2 is also moving, and ship 3 and ship 4. So basically what you see is that it's a very synchronized behavior. So that is different from what I show you in bacteria. They show highly synchronized behavior. So what can we do here? And what we can do is basically assume that there is this effect of imitation, and the question is how you can describe that mathematically, and this is, I will explain you how you can do it, or how you can do an experiment to put in evidence that there is imitation. Here what you have is a trained individual. This individual has a collar, a vibrating collar that you can activate remotely. You have a control, you press a button, and that collar will start vibrating. And this guy will learn that has to look for a yellow panel, because if moved to a yellow panel, it's going to receive a reward. So it's going to associate this vibration with reward, and it's going to move towards the panel. So now the question is the following. You have a group of static individuals. You have one with a vibrating collar. You call this guy start moving, induce the motion of the others. And now what you ask yourself is, what happens with an individual that is behind? Now has a bunch of guys moving. Let's say these 6 guys, or with more, 7, whatever, these guys that are moving, and many others that are not moving. So what we want to know is how quickly, or how the size, if stays in the current state or joins the others. And if you do that, let me show you a bit the experiment. This is the experiment. Hope that it works. Yes. Okay, so you will see around here, if I don't stop this, the tracking, the individual is around there. It will start moving towards this panel. You have 4 panels here. It's moving towards this one, and this is basically the data that you have. And now what you can do is you can measure how quickly each one basically, what the time it took for every individual from not moving to moving state, right? So that you can do from this experiment. You can also do with experiment I showed you before, because you can also have access to the state of the entire group at every instant. These are kind of technical details. At the end, you end up having a transition rate. The transition rate has a spontaneous transition rates that is, there's always some the individuals that are in your own state will try to inhibit the transition. The ones that are in the other state will try to basically excite you, promote the transition to that new state. So this is the form of the transition rate. You put that and you can reproduce basically pretty much of the data. So the last thing that we have to do is to use this behavior state to fit our equation of motion, but let me show you what happens. This is the data. These are the guys. It's a 1D representation of the data, head up, head down, motion, or stop. And then you have the others. Now it's a model that does basically reproduces the behavior. So as you can see, they also do similar stuff, head up, head down, motion, and so on. So, all right, so we have our model. So now let me tell you a couple of few things. I'm on the edge. Yes, 5. All right, so what I want to show you now is what they do as they are in a moving phase. When they are in a moving phase, I mean, there was something also information how they moved. Before it was a 1D representation. Now I want to see what happens a bit in 2D, and only when they are moving. So basically, I want to show you two things: is how information, how does information flow in the system, and what information is shared among these individuals. And so this is basically what we want to understand is how they do this, what is happening as they are moving in phi formation. So I give you just the result because there is not much time. What we found is that basically the individual that is in the front of the group doesn't care about anybody. The first follower only is interested on what is doing the leader. This third individual only cares about what is doing the first follower, and so on. So it's a chain. And if basically you are doing whatever is doing the individual that is in front of you. That's all. Now the question was whether they are using velocity or positional information. If they do velocity and you have this kind of chain, or if you do any of the other interaction networks I'm showing you here, you won't get phi formation. I mean, this line formation, you only get it if you get positional information. That, by the way, also implies that you will also get a velocity correlation between the individuals, because it will be also pointing in the same direction. Now, with this, you may wonder whether these things I show you was the result of just looking at 4 individuals, this phi formation and this behavior you can see in large groups. Of course, the problem is that it's very difficult to track this many individuals and so on, and you need a large space. So this is what you can see when you go to the mountains and you see these guys moving. So you also get these chains, polar chains moving around. Now, you can ask a couple of questions. What's the advantage, at least mathematically, of operating this way? And I'm going to give you I'm going to mention only 2 things. Let's assume that the individual that is in the front is informed regarding, for example, how to navigate a complex landscape and reaching this exit from this maze. I mean, that could be reaching a food patch somewhere in a forest. So if you do that, if they operate exactly in the way I'm showing you, I mean, with interaction network 3 and only exchanging positional information, they will be able to do it. Otherwise, they get lost in the maze. So this is exchanging velocity, for example. Here is operating with interaction network 3 and positional information. So it's the best way of navigating a maze. If you get the informed individual is the leader of the group. I mean, knows the way through the maze. Another thing that they can do, because they move and stop, is they also can do information pooling. And if they do information pooling through many collective motion phases, what they can do is, for example, the collective, the group, can in a more efficient way find a target than one can do individuals. So if each individual have an idea where is the target, but they are prone to have not the exact location, but with some error estimate of where it's located, now they can basically all together pool information and get in a more or less precise way where the target is. And so that's okay. All right, so this is connected to the wisdom of the crowd, or if you want, this is related to collective intelligence. Okay, so with this, I'm concluding. So for these guys, they take advantage of hierarchical strategies and democratic ones, if you want. And basically, I hope that I convince you that you can treat bacteria and shit in more or less similar way with these formalisms I showed you at the beginning. With that, I thank you. And these are the guys that helped me with all this.